அப்போ நமக்கு என்ன வந்திருக்கு அப்படின்னாக்க ஃபார்முலா எப்படி ரெடியூஸ் ஆகுதுன்றதை பார்க்கலாம். இதான் இப்போ நம்ம பார்த்த டெரிவேஷன். இந்த பார்த்த டெரிவேஷன் உங்க புக்ல இப்படிதான் இருக்கும். ஒரு சர்க்குலர் காயில்ல டிஎல்ன்ற செக்மெண்ட் எடுத்துட்டு அதனால எக்ஸ்ன்ற டிஸ்டன்ஸ் கூடிய பின்ற பாயிண்ட்ல ஏற்படக்கூடிய மேக்னெட்டிக் ஃபீல்டுடைய வேல்யூ பார்த்தாக்க வெர்டிக்கல் காம்பனன்ட் டிபி காஸ் தீட்டா ரெண்டு காம்பனன்ட் வந்து கேன்சல் ஆயிரும். ஹரிசான்டல் காம்பனன்ட் மட்டும் இருக்கும். ஃபார்முலா பார்த்தீங்கன்னாக்க மியூ நாட் ஐஏ ஸ்கொயர் டிவைடட் பை 2 இன்டூ ஏ ஸ்கொயர் பிளஸ் எக்ஸ் ஸ்கொயர் ஹோல் பவர் 3/2 அப்படின்னு வரும். இதுல நம்ம சில கண்டிஷன்ஸை போடுறோம். எக்ஸ் இஸ் ஈக்குவல் டு 0னா சென்டர் ஆஃப் த காயில் என்னன்னாக்க பாருங்க மியூ நாட் ஐ பை 2a அப்படின்னு வருது. அதே மாதிரி எக்ஸ்ன்றது ரொம்ப ஃபார் ஆஃப் டிஸ்டன்ஸா இருந்ததுனாக்க b is equal to mu naught I a square by 2x cube வருது. இதுலயும் நம்ம டைரக்ஷன் ஆஃப் த கரண்ட்டை வச்சு கரண்ட் ரூட்ல எந்தெந்த டைரக்ஷன்ல மேக்னெட்டிக் ஃபீல்ட் ப்ரொடியூஸ் ஆகுதுன்றதை ப்ரொடியூஸ் பண்ணலாம். மியூ நாட் ஐ பை 2πaன்றது ஸ்ட்ரெயிட் கண்டக்டருக்கு, மியூ நாட் ஐ பை 2aன்றது சர்க்குலர் கண்டக்டருக்கு அட் த சென்டர்ல. ஒரே ஒரு பை மட்டும் தான் மிஸ் ஆகுது. மியூ நாட் ஐ பை 2πa அப்படின்றது ஸ்ட்ரெயிட் கண்டக்டருக்கு, மியூ நாட் ஐ பை 2a அப்படின்றது சர்க்குலர் கண்டக்டருக்கு. இப்போ பி அட் தி சென்டர் ஆஃப் த லூப் பார்த்தோம். பி அட் தி சென்டர் ஆஃப் த லூப் பார்த்தோம். இந்த பி அட் தி சென்டர் ஆஃப் த லூப் when the plane of the coil is lying on the plane of the diagram, the direction of the current is clockwise, direction of the magnetic field is perpendicular. அப்போ இந்த மேக்னெட்டிக் ஃபீல்டோட வேல்யூவை நம்ம கால்குலேட் பண்ணிருக்கோம். இப்போ ஒரே ஒரு விஷயத்தை பார்த்துடலாம். ஒரு பாயிண்ட் சார்ஜ், ஒரு மூவிங் பாயிண்ட் சார்ஜ்னால நல்லா தெரிஞ்சுக்கணும், பாயிண்ட் சார்ஜ்னால ஃபீல்டு வராது, மூவிங் பாயிண்ட் சார்ஜ்னால வரும்.
Okay, so I want to tell you about calculating the magnetic field due to a moving point charge. Okay, so here's a moving point charge. It's moving to the right. It's got a speed v. And what we want to find is we want to find the magnetic field right here. And we already know its direction from the last video. The way that we find the direction is you take your right hand, you put your thumb in the direction of the moving charge, and then you're going to curl your fingers. And your fingers will tell you the way that the magnetic field circulates. And so, say right here, right in the plane of the page, the field is straight down. Yeah, it's straight down. Whereas over here, it's straight up. And so there are all these concentric circles going around. And so right within the plane of the page, this magnetic field is up. So it's nice. I put a dot there, and you can think of that dot as being the vector that's out of the page. I didn't put an X, which would indicate that it's into the page. Okay, so what you do to find this field then is you draw a vector from where the charge is, center of the charge, that's supposed to be a point charge, to the point where you want to know the field. And let's call that the R vector. And this is actually the V vector right here, the velocity vector. And, you know, what the strength of that field should depend on a few things. It should depend on the Q, just how much Q you have. It should depend on how fast you're going. So it's going to depend on V. It's also going to depend on R, how far away you are from it. And as we said in the last video, it should depend also on the angle that R makes with V. So the way that those all factor in is this way. The B, due to this, is just going to be, we're talking about the magnitude now and the direction, and you'll see how I get another way of getting the direction using the right hand rule. So it's going to be some constant, mu naught over 4 pi. I'll tell you about those constants in a second. Mu naught is called the permeability of free space, and 4 pi is just a constant. So it's going to be mu naught over 4 pi, then times Q, whatever this Q is. Maybe I'll call it a lowercase q over here. So Q times V. Now I'm going to say cross R. And then I'm going to divide this all by R cubed. Just the magnitude, the length of this times R cubed. Now you might think, can't these cancel out? And they do. In fact, some books write this as QV sine of theta, and then they cancel out the R's, and this is just R squared. I might teach it that way a little later on. But for right now, the reason why we have this cross R here is to give you the cross product. When you do a cross product of V cross R, when you have the tail of V and the tail of R together, then to figure out the cross product, that's going to give you, that's how you get B. You just take your right hand and you're going to sweep from the first vector to the second vector. So V to R, you're going to just sweep across, and the direction your thumb is pointing, that's the direction of the magnetic field. So if you take your V cross R and you sweep it across, the direction your thumb is pointing is the direction of the magnetic field. That's why the magnetic field is up. So we have two ways to figure out the field's direction. We can do V cross R, or we can do on this right hand rule that tells us that, yeah, at the plane of the page, it's coming up. Now if you're wondering about, like, say right here, it's going that way, and right in here on this side, it's going to be going into the page. Let's see if the cross product would give us going into the page. I would take my V cross R. My R is shooting this way this time, so I'd have to, you start at the first vector and you go the shortest distance to sweep to R. So the shortest distance would be sweeping this way, and you see how you probably can't see, but my thumb, when I do that, see the thumb, it's pointing in, and so right there it's pointing into the page. Okay, so two ways to figure out the cross product direction. Okay, so another way of writing this then is sometimes people will do this. They'll say it's equal to mu naught over 4 pi. And you know how the cross product gives you the sign? So you can do Q times, now I'm only talking about the magnitude now. The magnitude of B will be mu naught over 4 pi times Q times V R sine of theta. But I'm going to cancel out that R, that QVR sine of theta. I'm going to cancel out with one of these. So it's, sometimes you see it written like this too. This isn't as good because it doesn't give you the direction. Then you need to use your right hand rule to get the direction. But this is the magnetic field that's due to this. Hey, notice that how do we get the biggest field then? To get the biggest field, we want to make Q really big. We'd like to make V as big as we can. And the angle, it'd be nice if the angle were 90 degrees, because the biggest sine gets is 1. And it does that when it's at pi. And so like right here, we'd like to be close, have this go real fast, and like right here, right there, that's where the field is the strongest. Actually right here too. And actually, I'm not drawing this in 3 dimensions, but a little bit above the charge and a little bit below the charge, we have these really strong magnetic fields. Okay? So, as a matter of fact, along the line, if I wanted to know the field along this line, say right here, then I draw my vector R, and you see how the angle between V and R is 0? So when you do, how much of V is perpendicular to R? Remember, the cross product gives you the part of V that's perpendicular to R times R. And so how much of V is perpendicular to R? And the answer is none of it. So that turns into 0. So no field all the way along this line right here. But there is field here. It's just not as strong as the field right here. Okay? So when you do this, if Q is in coulombs, Q is charge, and we'd like that to be in coulombs. How do I want to designate this? I'll just say it's in coulombs. And if V is in meters per second, And if R, the distance, is in meters, then what you get is B will be in Teslas. One other thing then about mu naught. Mu naught is called the permeability of free space. Free space is another word for a vacuum. So it's the permeability of free space. If you're in a different substance, you would use a different mu naught then. And it turns out that the value of mu naught it's 4 pi times 10 to the negative 7th. Now we can work out the units in a bit, but that's the magnitude. And when you divide that by 4 pi, you can think of this whole thing just being, you see how that turns into 1 times 10 to the negative 7th? That's what that turns into. Okay, and maybe in another video we'll talk about what these units actually are. Okay, so
இப்போ ஒரு சார்ஜ் வின்ற வெலாசிட்டில நகர்ந்ததுன்னா அதனால ப்ரொடியூஸ் ஆகக்கூடிய ஃபீல்டு என்னன்னு பார்த்தோம். பயோட்-சாவர்ட் லாவில் ஐடியல் எடுத்துட்டு ஐன்றது கரண்ட். கரண்ட்டுக்கான ஃபார்முலா வந்து Q/T, ரேட் ஆஃப் ஃப்ளோ ஆஃப் சார்ஜ். Q/dt வச்சுட்டு dl/dt Vன்னு போட்டோம்னாக்கா QV cross Rன்னு வந்துடும். வெக்டர் கிராஸ் ப்ராடக்ட் எக்ஸ்பேண்ட் பண்ணனாக்கா QV sin θன்னு வந்துடும். அதுல இருந்து பாத்தீங்கன்னாக்க ஒரு சார்ஜ் வின்ற வெலாசிட்டில நகர்றப்போ ஃபீல்ட் இருக்கக்கூடிய டைரக்ஷனுக்கு பர்பெண்டிகுலரா சார்ஜ் நகர்ந்ததுன்னா மேக்சிமம் sin 90 இருக்கிறப்போ ஃபீல்டு மேக்சிமமா இருக்கும். Qன்ற சார்ஜ்னால வின்ற வெலாசிட்டில சார்ஜ் வெலாசிட்டிக்கு பர்பெண்டிகுலரா நகர்றப்போ ஃபீல்டு மேக்சிமமா இருக்குன்றத சொல்லிட்டு அடுத்ததுல தொடர்ந்து பார்க்கலாம். ஆகவே முதல் பகுதியினுடைய 4வது பார்ட்டுக்கு வரும். ஐன்ற கரண்ட் டிஎல்ன்ற செக்மெண்ட் வழியா போறப்போ ஐடிஎல்ன்றதுக்கு பேரு கரண்ட் எலிமெண்ட்னு பேரு. அந்த கரண்ட் எலிமெண்ட்ல இருந்து தீட்டான்ற ஆங்கிள் Pன்ற பாயிண்ட் ஆஃப் அப்சர்வேஷன் ஆர்ன டிஸ்டன்ஸ்ல இருந்தா dB is equal to mu naught by 4 pi ஐடியல் sin theta by r ஸ்கொயர்ல இருந்து பயோட்-சாவர்ட் லா அப்ளிகேஷனை யூஸ் பண்ணி நம்ம என்ன பண்ணணும் அப்படின்னாக்க ஒரு இன்ஃபைனைட் கண்டக்டருக்கு என்ன கண்டுபிடிச்சோம்? மேக்னெட்டிக் ஃபீல்டு கண்டுபிடிச்சோம். அந்த மேக்னெட்டிக் ஃபீல்டோட வேல்யூ என்ன வந்ததுனாக்க mu naught I by 2 pi r வந்தது. ஆருக்கு பதிலா ஏன்னு வச்சுக்கலாம். இப்போ நல்லா கவனிங்க, இந்த பின்ற மேக்னெட்டிக் ஃபீல்ட், அதாவது ஒரு இன்ஃபைனைட் கண்டக்டர்ல இருந்து ஏன்ற டிஸ்டன்ஸ் இருக்கக்கூடிய பாயிண்ட் ஆஃப் அப்சர்வேஷன்ல மேக்னெட்டிக் ஃபீல்டோட வேல்யூ கரண்ட்டுக்கு டைரக்ட்லி ப்ரொபோர்ஷனலும் டிஸ்டன்ஸுக்கு இன்வெர்ஸ்லி ப்ரொபோர்ஷனலா இருக்கலாம். டைரக்ஷன் ஆஃப் த பி மேக்னெட்டிக் ஃபீல்டோட டைரக்ஷனும் டிஎல் கிராஸ் ஆருடைய டைரக்ஷனும் ரைட் ஹேண்ட் ஸ்க்ரூ ரூல் படி கண்டுபிடிக்கப்படலாம். அது எப்படி இருக்கும்னாக்க இட் இஸ் perpendicular to the plane of the diagram and entering into the plane at P. Entering into the plane at P. நல்லா கவனிங்க, ஒரு கரண்ட் முதல் படத்துல பாத்தீங்கன்னா ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் மேல போகுது. அப்ப கர்லிங் ஃபிங்கர்ஸ் பாத்தீங்க அப்படின்னாக்க எந்த டைரக்ஷன்ல இருக்குன்னு பாத்தீங்க. ரெண்டாவது படத்துல கரண்ட் கீழே போகுது, மேல இருந்து கீழே போகுது. இப்ப கரண்ட் டைரக்ஷன் எப்படி இருக்குன்னு பாருங்க. கரண்ட் டைரக்ஷன்ல மேக்னெட்டிக் ஃபீல்ட் டைரக்ஷன் எப்படி இருக்குன்னு பாருங்க. அப்போ கரண்ட் மேல போறப்போ ஒரு ஃபீல்ட் டைரக்ஷன், கரண்ட் கீழே வரப்போ ஒரு ஃபீல்ட் டைரக்ஷன். அப்ப இன்ஃபைனைட் கண்டக்டருக்கு ஒரு ஃபார்முலா கண்டுபிடிச்சிருக்கோம். B is equal to mu naught I by 2 pi A. இது அந்த வயருக்கு பல்வேறு வடிவங்கள் வருகின்ற போது இந்த ஃபார்முலா எப்படி மாறுதுன்னு பார்த்தோம். இந்த வயரை ஒரு சர்க்குலர் லூப்பினுடைய ஒரு வடிவமா எடுத்துக்கிட்டோம்னா ரொம்ப ஈஸியா இதை கண்டுபிடிக்க முடியுதுன்னு பார்த்தோம். இப்போ சர்க்குலர் லூப்புக்கு அந்த மேக்னெட்டிக் ஃபீல்ட் என்ன இருக்குன்றத கண்டுபிடிக்க முயற்சி செய்யலாம்.
Okay, this video is on the magnetic field on the axis of a circular hoop. Okay, so what about this magnetic field on the axis of a circular hoop? Here's a circular hoop. It's got some current in it. Let's say the current is going around like this. That's the I through it. It's going around like this. This part is closer to you than this part. And they want to know what the magnetic field is, say, right here. Okay, so let's call the radius of the hoop R. So the radius from there to here is going to be capital R. Okay, so what we do is we use the law of Biot-Savart. We're going to break this into, let's just analyze one little segment of this. A little segment DL. And DL is coming out this way. That's the direction of DL. Coming out that way. It's actually pointed in the negative y direction right now. At the top, it's pointing in the negative y direction. And here I'm going to draw a line that goes straight down to this point. Okay, let's call this distance x. And I'm going to tell you that the field, just due to that dl, if you take your right hand and you put it in the direction of the current, then, and you curl your fingers, then it's going to be a circular field just due to dl, and it's going to point this way. It's going to be at a right angle to this, so it's going to be like that. Okay, now that's going to be called, we're going to call that the magnetic field just due to that dl, so that's going to be a dB. Now, let's look and see what is the magnetic field due to this dl down here. This dl is heading this way. It's heading in the positive y direction. It's heading that way. And if I take my fingers and curl them like that, then right here, if I were to draw a vector from here to there. Now those look like they're in the same direction, but the dl there is actually perpendicular to this vector. And the magnetic field for this is going to be diagonally downward, again at a right angle. So this is going to be at a right angle. And so is this one. This will be at a right angle too. Okay. Now the magnetic field then, due to those dLs, if we wanted to figure out the magnetic field just due to the one, we'll use the law of Biot-Savart. dB is equal to mu naught times I. We're going to say that we know the I in this ring. So it's mu naught I times dl times the sine of theta. This is the law of Biot-Savart over 4 pi times this distance squared. Now what should we call that? Let's call that little r squared. Okay, this distance we're going to call little r. That's this distance as well. Okay, well, you see, that's the magnetic field from this little dl up here, but here's the problem. Each one of these little dl's, as you go around, they each point in a completely different direction. So this one points that way, the dl from this points that way, or excuse me, the dB from this points that way. So they're all, it kind of forms a TP around here if you think about it. And for every one up here, there's one down here that's going to cancel. So like this part's dB, say y in this case, or z rather, that's dBz. Yeah, dBz is going to cancel with this one, that dBz. So those are going to cancel, and what you're going to be left with is just for these two at least, is you're going to just be left with the x components. In fact, you're going to be left with the x components for all of them. Okay, so I'm going to say that you only use the x component. Well, the x component is going to be times the cosine of that angle, theta. So that would be, if I wanted just the x component, then I could really add them. And that's going to be times the cosine of theta. That's what gets me where this is theta. Okay, well, what I'm going to do now is I'm going to sum those up with an integral. So I have to sum these up. So when I sum these up, I get dBx. I guess I should let you see this equation. There it is. dBx is equal to mu naught I dl. Now that's sine of theta. This is the angle between dl and r. And so that sine of theta is that theta there. That's a different theta than this one. So I'm going to call this theta 1 and theta 2. And theta 1 is the angle between dl and r. And I'm going to argue that that's a 90-degree angle. So you don't, the sine of 90 is just 1. So that's going to just turn into 1. It's always at a right angle. It's tough to see in my drawing, but dl, that little vector, is always perpendicular to r. Okay, now, so I'm getting rid of that. And then I got the cosine of theta. But you know, theta doesn't change in here. No matter which dl I'm at, theta, this theta is always the same angle. Same size of angle, at least. And so it's mu naught I dl cosine of theta. And then that's going to be over 4 pi and then r squared. Okay, to get the entire magnetic field then, the entire magnetic field is just going to be summing these all up with an integral. Okay, but you can pull out anything that's not you can pull out any constants, and so the mu naught's constant, I is a constant, the theta is a constant, so is the r a constant. So when I pull those all out, I'm just left with mu naught I cosine of theta all over 4 pi r squared, and you're summing up all the dl's. Well, to sum up all the dl's is just going to, when you sum all these little guys up around the circle, that's going to just give you 2 pi capital R. So that's going to be, the b around there is going to equal mu naught I cosine of theta times 2 pi capital R all over 4 pi r squared. All right, now we would like to, what we're going to do, we're done, but I want to change that theta into terms with little r's and big R's and stuff in it. Okay, so let's take a look at theta here. Okay, remember this is a right angle. The angle that B makes with the r vector, it's always going to be a right angle. And this straight line is 180 degrees. This is 180 degrees from here to there. And so if that's theta and that's a right angle, then this has to be the complement of theta. This is 90 minus theta. And if this angle is 90 minus theta and that's a right angle, then this is theta. We're back to theta. And so we can say that the cosine of theta, if I want to substitute in, the cosine of theta is the adjacent side divided by the hypotenuse. So the cosine of theta is the adjacent side, that would be capital R, divided by the hypotenuse, little r. So I'm going to put that in for that. So as it turns out, that B, almost done here, B is going to equal mu naught I 2 pi r over 4 pi r squared, and the cosine of theta we said was capital R over little r. Okay, now I'm just going to sub in then for r, for lowercase r. Isn't lowercase r this guy? Isn't it r squared plus x squared? So it's, well, the square root of r squared plus x squared. So I'll sub in for that, and then I'll be done. So sub that in, and that's it. Thanks. Bye.